Good afternoon, this is Schweitzer. We're going to discuss a couple things here about one type of a reaction that we're highlighting in this chapter. It's called a solubility reaction. So the first thing we're going to do is we're going to really just highlight what it means to be dissolving. Okay, now some things dissolve differently than others. This is not the first time we've seen this, so this is kind of a review. So write the reaction, the solubility reaction for each substance above and draw the representative model. Okay. So anytime that you can do something on your own without me, I would strongly encourage you to pause the video and then do it, and then watch me do it. So NaCl, the equation would be NaCl goes to, there you go. And of course, this beaker is one model, and of course this is just another model. This is trying to mimic what's happening in the beaker. The beaker is trying to mimic what's happening in real life. How many of those do I got to draw? You can draw as many as you want. Okay, but in that case, make sure it's 1-to-1 ratios and make sure they're separated. Aluminum chloride. Okay, aluminum chloride. And it goes to aluminum, and it's a +3. Gotta have those charges on here. +3 Cl minus. I just balanced it. So in this case, I'd have 1 aluminum. Now, why are the charges on there? Because that's what's allowing it to dissolve. I can hide that in a minute here. In a second, let's just finish up this drawing. And of course, it looks like that. And I can have as many as I want here, but it's going to come in this package. 1 to 3. Okay, so in this case, just a quick highlight that charged atom would attract a water molecule. So this is another version of this model would be just to like add in a water molecule. What would it look like? Okay, so it might look like something like this. Okay, or it might look something like this. You'll notice that I have the positive end of the water molecule because it's polar, connecting to the anion here, and the negative end going to the positive ion. We call this an ion dipole attraction between these charged ends. Either way, okay. Let's go ahead and look at this one. Now, this guy, you notice, is sugar. Sugar dissolves very nicely, but it is not ionic. So it'd just be C12H22O11, let's say solid, is just going to go to C12H22O11, and then we just say aqueous. And I'm going to use X equaling C12H22O11. I may have misspoke a second ago. This is not glucose, this is sucrose, which is common table sugar. Glucose is half of that, approximately. And so I'm just going to draw like this. Okay, and you can dissolve a lot of sugar in water. So this is a pretty big substance. Dissolves nicely in water, which means it must also attract to water molecules. So little water molecules can really attract nicely to sucrose and therefore kind of prop them up into the solution. So you have little water molecules all around here grabbing onto it and just sort of holding it in the solution. All right. So some things are more soluble than others. Okay, and write the soluble reaction for each of these substances and draw the model above. Okay, this one I just did, so I either might change it or I'll leave it alone. Okay, but give me 1 second here. All right, so because we just did that when we swap it out. Okay, so let's see what we got here. So this guy now is a pretty big substance, xenon hexafluoride. Kind of a unusual substance, and might not be super stable, but it would just dissolve in maybe very little quantities, but it would stay together. And like that. So it's going to be xenon hexafluoride goes to, essentially could be a gas, it is a gas. It would go to xenon hexafluoride aqueous. Silver chloride, and is ionic, so it's going to dissolve into Ag+, plus Cl minus. So some things, sometimes very big things can dissolve nicely, and sometimes small things can dissolve nicely. Some things, big things, can't dissolve nicely. Now this is a substance that really doesn't dissolve real well. So sucrose dissolved extremely well, and this stuff probably sparingly. But here we have a substance that really doesn't dissolve really all that well, even though it has charges. So one of the reasons why something really big might not dissolve is literally because it's really heavy or more massive. This is a massive atom. Okay, look at its molar mass. Its molar mass is over 100. So heavy metals, sometimes they call them heavy metals, they don't dissolve very well. And only a little bit, but everything dissolves a little bit. Okay? And once it's fully maxed out, we would see stuff on the bottom. And we'll probably talk more about this later, but this means it's saturated, which means that essentially the maximum amount that could be in there at that temperature is there. All right, so with that being said, let's go on here. So add enough solid to create a saturated solution. All right, so I would suggest right at this point, it's your turn for student practice to try this out. I got 3 of them here. Take a moment and go ahead. Pause the video and try it. All right, so this guy is lead nitrate. Even though lead's big, it is pretty soluble. So I'm going to just go Pb2 plus, maybe NO3 minus, NO3 minus, solid on the bottom. There we go. NPbNO3, 2. All right, NaCl. Right? Very soluble substance. We'd have still at some point, we had enough of it where we could have stuff on the bottom. NaCl. All right, lead chloride, not very soluble. Right? Pb2 plus, Cl minus, and there we go, PbCl2. All right, let's go to the next page. Okay, so what happened if we mix these 2 substances together? Now again, lead nitrate is very soluble. Okay, sodium chloride is very soluble. But as we mentioned in the last one, that this guy here is very insoluble. Doesn't dissolve very well. So this guy here, I could probably have lots of these guys in here, and I can literally just crowd the heck out of this thing before I get so maxed out. And you know, I mean, salt's very soluble. This one too. I get lots of these things in here. So this one is very soluble. And this one is very soluble. But this one is has very low solubility. And you notice there's parts of these 2 that are in this one. Okay. So the question might be here is, how do I go from, if I mix these 2 together? If I mix 2 together, well then all of a sudden I have a compound solution that looks something like the thing we just had, where these 2 don't dissolve very well. Okay. So in this case, what would happen if we mix together 2 beakers together? And this is a really kind of an important idea. Different combinations of different ions have different solubilities. So now when I put this lead chloride together, the lead ions and the chloride ions grab onto each other or attract to each other a little bit better than the other ones do, and therefore they drop out. In order to drop out, we really just need to have an attraction between this guy and these guys. If they attract by Coulomb's law or Coulomb attraction, then they'll go out. So in this case, I'm going to get this situation, okay, where essentially we might think of at some point lead chloride PbCl2 is essentially maybe even being not soluble or even insoluble. Everything will dissolve a little bit. So I have all these cations and anions around here. I'm going to call these guys cations and anions. The sodiums and these nitrates, okay? They aren't really doing anything for us. They dissolve nicely. But we're going to have on the bottom here PbCl2. And again, if PbCl2, we generally consider to be insoluble. But because lead has shown to be a toxin to human beings, even very small amounts of soluble lead in the water can cause a lot of problems, not if you drink it once, but if you drink it over a long period of time, or a lot of it over a short period of time. We don't want to be drinking this stuff. So if it was something that was very vanilla, didn't do much, we might even not even consider it to be there. But because it is toxic, then this is something that people are looking for, even small amounts. So when something says PbCl2 is insoluble, does not form aqueous compounds, it does do a little bit. Everything dissolves to its maximum solubility and then will precipitate beyond that point down here. So when something says it's insoluble, it's not true. It is. It's just very small to where people just consider it to be insoluble. But there's something to be understood there. Alright, so I mixed these two together, and these different combination ions formed something that was quite attracted to each other and dropped out. Alright, let's try another one. And how can we model this? This essentially is a solubility reaction. Solubility reaction is one where we mix two things together and produce something that a different combination of ions that isn't going to be soluble. So here I have a cation, two sodiums, and a carbonate. Here I have a barium and two nitrates. Okay. And let's model above what happens. I mix the two together, and in this case, the barium and the carbonate attract very well and do not dissolve very well. So I'm going to get solid barium carbonate here. And my two sodiums, which are here, will just be up here, still dissolved. And I'll put the Ne on there. And my two nitrates, NO3 minus, they're also dissolved. So let's model above, and if we mix together, what happens? Just do that, okay? How might we model this? Okay, now, this is a model that we're going to use a lot for this particular type of reaction. Two dissolved, so this now doesn't say AQ on here, but they're dissolved. So solutions, two liquids we're going to pour together. And we're going to see, is there a different combination of different ions that have different solubilities? Now, just because I put something on paper here doesn't mean it's going to happen in the beaker. So I got to be able to look and see what those things are. But my opportunities are this cation could have opportunity to precipitate with this anion. And this cation could precipitate with this anion. And that's why I have these two options here. I'm not going to have an option of two cations precipitating. Let's try this out here. Okay, AB is Na2CO3. I like to put these on here because they're always on there and they're there. So I like putting them on there. You don't have to, but and there's barium nitrate. Okay. And then this is going to be +2, and this is -1, and there's a 2 here. So I want to. How do I predict my products? So predict my potential products. What I do is I follow this template. Okay, so sodium and nitrate, sodium and nitrate. Now keep in mind, put the charges above them so that when we charge balance, we don't have the 2 there. That 2 is there because of that 2. This one doesn't have the 2, so it's just NaNO3. This 3 is part of the nitrate. And then I have barium, which is +2. And the carbonate is CO3 -2. and charge balance. You might say to yourself, well, what happened to the 2 nitrates? There's only 1 here now. That will work itself out in balancing. So 2 goes there, 2 sodiums, and I'm done. Now keep in mind, even though we wrote this together, think about, this is just a model, and not every model is perfect. So look at what it looks like in the beaker. Okay, are the sodiums and the nitrates even together? No. If you evaporate out the water, they would come together. Okay, but in this case, if I filtered this thing, these guys would go through the filter, and this would get removed. So in this case, we label this as being aqueous, and this as being solid. Okay. Note, barium carbonate is not soluble, and sodium nitrate is soluble. Now, when I want to drink this substance, when I want to filter it off and assume there's no barium, there's still a little bit of barium in there. It's not the best thing to be drinking as a heavy metal. Otherwise, okay, so I just showed an example where we're using this model, okay, of a solubility reaction. And then we're going to label whether they're aqueous or solid. We're going to learn here in a short time how to know if it's aqueous or solid. Okay. All right, here we go. Try another one. Okay, so now I'm going to react magnesium sulfate reacts with barium sulfate. Now there's a solubility chart in your workbook. Okay, and I'm going to have mine on here, but you should know where that is. Sometimes we would use it on our quiz, or we would use it on a test, and sometimes we'll provide them, but you have one. Okay, I'm going to show a few different versions of how this works. Okay, now again, I'm following the model right here. This guy right here, this model. Okay, so you got it. I'm going to use it. All right, so magnesium sulfate is MgSO4 plus 2 minus 2, charge balanced, plus barium sulfide plus 2 minus 2. Done. Yields. What are my new options? Magnesium sulfide, and barium sulfate. Again, plus 2 minus 2, plus 2 minus 2. That one worked out just as is. Okay. Now, for all of these guys, I have to indicate whether it's aqueous or whether it's solid. So whether it's aqueous or whether it's solid. Okay, let's look at our typical solubility chart. This is what we use for our solubility chart. I'm going to walk through this thing pretty quickly, but typically on your sheet, there's a QR code that will walk you through how to use this chart. I'm not going to do that here too much, just a little bit, okay? First things first, quick check. These guys, if any of these guys are present, it's always aqueous. So you can't see that bottom one, it's a nitrate and ammonium. So anytime you have one of these guys present, again, let's say NaCl, this has got sodium on it. So this one generally dissolves nicely, which of course you know it does. Okay. So then insoluble, okay, so anytime we're dealing with this thing, we're dealing with a cation and an anion. So this chart here, for the most part, deals with the anion, whether it's present or not. So carbonates generally are insoluble. Okay. Here's the exceptions, and this is referring to the cation that's on the front side of the carbonate. So what's the cation? You have the cations sodium, potassium, ammonium, which is quick checks. This would be exception, which is aqueous. All right, so sodium carbonate dissolves nicely. I put an S there just to remind myself of that. Okay, these anions, for the most part, are soluble. So, and these are the exceptions. So let's take a moment and walk through our example of this. Okay. Magnesium sulfide, barium sulfate. First thing I do is, do I have a quick check? Maybe sodium, potassium, ammonium, or nitrate. I don't have any of those. Sometimes it's nice to be able to see that and go right to it. Get it done. All right, sulfides. Sulfides are generally insoluble. What is the exception? Magnesium exception. This is going to be aqueous. Let's go back to that guy and put an AQ in here. Barium sulfate. Okay, sulfates generally are aqueous. They dissolve nicely. Exceptions would be barium. Okay, barium section is going to be solid. Okay, let's go add that one. So this guy is going to be solid. All right, so let's make this here now. So MgSO4 is going to be Mg plus 2 SO4 minus 2, barium plus 2, sulfur minus 2. Put them together, and we're going to get barium sulfate, and I put what's we got here? So yep, barium sulfide. All right, so then we're going to have, in this case, magnesium ion still floating around, and the sulfide ion still floating around. And that's just a generic example. Okay. Now I have three different types of equations. Molecular version, very common, have to have those states on it. And balancing is pretty simple. What's the ionic version? Showing it really what it actually is. This is probably the least common version, although it's the most accurate. Alright, show means ions that are actually showing separate, we show them as being separate. Alright, so I'm going to show all this stuff as being separate, and then I will show the fact these two they didn't come together, they stayed separate. Mg plus 2 plus sulfur minus 2, and then the barium, I'm going to put it together because it actually is together. Okay. Not as common. Net ionic removes spectators. So removes what's called spectator ions. What are spectator ions? They're the ones that didn't do anything. So the magnesium in the magnesium is a spectator ion, it didn't do anything. The sulfide is a spectator ion, it didn't do anything. What actually happened? Well, the barium and the sulfate came together to form a solid. That's what happened. So remove spectator, remove spectator, remove spectator, remove spectator. And what's left? Sulfate plus barium yields barium. And that's called the net ion equation, which is also extremely common. All right, here we go. There's our solubility chart. And let's try another example. Pause the video and try it on your own. Okay. Now start moving a little bit faster now. All right, potassium hydroxide. That's KOH plus PB. It's positive 4. I like to put my charges above them. And it's chloride, Cl4. This is going to be my options, PB, OH, and plus 4 minus 1. It's this guy and that guy. 4 plus KCl plus 1 minus 1. Now, what about these 4s here? It'll come out and we balance it. So 4 chlorines, 4 chlorines, 4 potassiums, 4 potassiums, 4 hydroxides, and 4 hydroxides. Okay. Let's go to our solubility chart. What do you know about hydroxides, potassium, chloride? We have a quick check here. Potassium is here, a quick check. This one's going to be aqueous. And I like the quick check because it allows me to get a lot done quickly. This guy, hydroxides. Let's go to hydroxides. And hydroxides here, generally insoluble, and these are the exceptions. Lead, I don't see lead there, so this thing is just going to remain insoluble. All right, ionic. Okay, plus OH negative yields PB plus 2 plus Cl minus. Now, I don't even put the 4 on there. It's just the way we do it. You could balance it, put a 4 up front. You put a 4 on the bottom, that means you're assuming there's a cluster of 4 chloride ions. That's just not the case. There are 4 individually floating around chloride ions. Yields, okay, PbOH4 plus K plus Cl minus. Let's draw this out. K plus OH negative Pb2 plus Cl minus, Cl minus, Cl minus, Cl minus.
Alright, now I would need more of my hydroxides to match up with these guys, so 2 of them is pretty skimpy. So I'll draw a few more of these guys in here just so I have some hydroxides to grab onto. And there we go, I drew 4 of them. So all 4 of these hydroxides, we're going to grab onto one of those guys. So one of these guys, to form 1:4 ratio, grab onto this one, this one, this one, and that one, to form a solid PbCOH parentheses 4. Everything else is floating around. 4 chlorines, and use a dash for that. And then 1, 2, 3, 4. 1, 2, 3, 4. Positive equals K. Okay. What's my net ion? Who are my spectators? It's going to be OH negative. There would need 4 of them. Plus, I want that to be a plus PB, and this is plus 4. Just make sure we're getting that. We need plus 4. That's because it's plus 4. Charges aren't changing. Just produces PbOH4. Okay. There's mud. All right. Next up, pause the video. Give it a try. Okay. Now this guy here is going to be potassium nitrate, KNO3 plus calcium chloride, CaCl2, plus 1 minus 1 plus 2 minus 1. It's going to give me potassium chloride and calcium nitrate. Okay, so I need parentheses 2 here because this is a plus 2 and a minus 1. Plus 1 minus 1. Okay. Alright, let's check these over for solubilities. And you might notice that this is a quick check, so it's going to be aqueous. And this has got a quick check, so this is going to be aqueous. So our question here is, what if there's no solid produced? Okay, let's sketch this out. I have K plus NO3 minus. I have calcium plus 2, Cl minus, Cl minus. I dump them together, and I get K plus NO3. Spread that out a little bit. K plus NO3 minus. Okay. And then I have the 1 calcium plus 2, and then Cl minus and Cl minus. Okay. So on this point here, you'll notice that if I wrote my ionic equation, it would be K plus NO3 minus plus Ca plus 2 plus Cl minus yields potassium plus Cl minus plus calcium plus 2 plus NO3 minus 1. Everything stayed separate. Everything stayed separate. Well, if I cross out my spectators, I literally would have to cross everything out and there would be nothing left. So when we have no new substance, then this would be deemed as we need something to change here. No reaction. No precipitation reaction, at least. So look for 2 aqueuses, and that means no reaction. Just nothing happened. Just mix them together. Alright, let's try another one. Sodium hydroxide. Again, pause the video, run it through yourself. So I have NaOH plus hydroiodic. Opportunity to try that out. HI. And we're going to get cation, anion, cation, anion, NaI, NaI. Now right away, that's got a quick check. I'm going to put aqueous on it. Plus HOH. And you'll notice that HOH is just kind of an odd or fancy way of writing water. And we want this to be a liquid. So there's no solid being produced. There's no solid. But do we have a new substance? And the answer is yes. Water is our new substance. So let's draw it out. Na plus OH negative. I got H plus I negative. And I'm going to get water, and then the Na plus is still floating around, and the ion negative is floating around because it's aqueous. So my ionic is going to be Na plus OH negative yield plus H plus I negative yields H2O if you'd like plus Na plus I negative. My net ionic is going to be H plus OH negative yields H2O. Okay. And that's getting towards the end of all our variations, and that is it. We'll stop there. Your option now is to go to our workbook and try a bunch of questions out like these, and they're just going to be more of the same of this. Thank you very much.